speaker is Daniel Stiven Posada from CIMAT, who is going to talk about foliations on projective K3 surfaces.
Okay, thanks. Thanks for stay here. Thanks to organizer for accepting my talk, and Professor Frank, happy birthday. My talk today is a joint work with Jorge Olivares. I want to divide this talk into 5 parts. First, I will begin with basic definitions and the main questions to be addressed in this work. Next, I will present you the previous results that we know about the solutions, or some solutions about the problem. Next, I will present you our results and the relation with the Poincaré problem. Next, I will present you a work in progress in this moment about results in a more general setting. To finish with future directions or works. Okay, let me start with the definition of the concept of foliation by curves. Given a complex manifold M, for us, a foliation by curves on M is a non-zero morphism from a line bundle on the complex manifold to the tangent bundle of the complex manifold. 2 different morphisms can define the same foliation, and that is the case if and only if the line bundles are isomorphic and there exists a non-vanishing holomorphic function on the complex manifold such that S prime is equal to F times S, where S prime and S are the sections that define the foliations. In this case, we say that the line bundle is the tangent bundle of the foliation, and for this, the foliations by curves are an equivalence class of these sections defined by this relation, equivalence relation. Since in a compact manifold, the only holomorphic functions are the constants, so if our complex manifold is compact, the space of foliations on the complex manifold with tangent bundle L is the projectivization of this cohomology group. And that is isomorphic to this. Another important concept is, given a section, the singular scheme of the section is the scheme of points on the complex manifold where the section vanishes. Since a foliation is an equivalence class of those sections, so the singular scheme of a foliation is the singular scheme of any section in the equivalence class to define it. And we say that the foliation has isolated singularities if the dimension of that singular scheme is 0. That is, the singular points are just points, not a curve, not a surface, no, just points, isolated points. And we say that the foliation is uniquely determined by its singular scheme if the foliation is the unique foliation with its singular scheme. That means whenever another foliation has the same singular scheme, so the foliations are the same. With this, fix a complex manifold, and given a line bundle on the complex manifold, the main questions of this work is, when do there exist foliations by curves on the complex manifold with tangent bundle L? Next, when are such foliations uniquely determined by its singular scheme? Okay. Previous results. When the complex manifold is a projective space, so the line bundles on the projective space are given by this form. This is the line bundle. Sorry. This is the line bundle where the global sections are the homogeneous polynomials of degree 1 minus d. And the foliation is with a foliation with reduced singularities. That means isolated singularities, but the singular points have multiplicity 1, theme points. So Gomez-Mon and George Kempf proved that the foliations are uniquely determined by their singular scheme if and only if d is greater than or equal to 2. In a more general setting, when the complex manifold is a compact projective simple manifold, simple means that the tangent bundle is simple, and that means that the global endomorphisms of the tangent bundle are the scalar multiples of the identity. Let L be an ample line bundle on the complex manifold and a foliation with isolated singularities. So there exists an integer such that for any integer greater than or equal to this, the foliations are uniquely determined by their singular scheme. In particular, the Gomez-Mon and George Kempf theorem holds just for isolated singularity. So the reduced hypothesis was not necessary. For this, it's important to see the simple manifolds. Examples of simple manifolds are the Calabi-Yau varieties, and the first example of that are the K3 surfaces, Calabi-Yau varieties of dimension 2. Another preview results is when the complex manifold is a Hirzebruch surface, the line bundles are of this form, and the foliations have isolated singularities. So if the invariant of the Hirzebruch surface is equal to 1, the foliations are uniquely determined by its singular scheme, by their singular scheme for most line bundles. But when the invariant is greater than 1, that is not true in general. No, that is not true. However, if two foliations share the singular scheme, so there exists a global invertible endomorphism of the tangent bundle of the Hirzebruch surface such that the sections that define the foliations are related by the endomorphism. Okay. To study foliations in this case, we need a complex manifold and we need to study the line bundles on the complex manifold. In this work, we will work with projective K3 surfaces, but what is that? A complex K3 surface is a compact connected complex manifold M of dimension 2, because there is a surface, such that the canonical bundle is trivial and the first cohomology group of the structural bundle is 0. And an algebraic K3 surface over C is a complete non-singular variety M over C of dimension 2 such that the same conditions hold. So we have two different definitions in two different worlds. What is the relation between both definitions? Since the projective space admits both algebraic and complex structure, then the GAGA gives us a natural embedding from algebraic K3 surfaces over C to complex K3 surfaces, whose image is precisely the complex K3 surfaces that are projective. For that reason, in this work, we focus on projective K3 surfaces. And therefore, the algebraic and complex viewpoints coincide for us. Okay. One example of that. This is a proposition. The only projective K3 surfaces that are complete intersection in a projective space are the following: a smooth quartic surface in P3, a smooth complete intersection of a quadric and a cubic in P4, and a smooth complete intersection of 3 quadrics in P5. We have fixed the complex manifold, so now it's necessary to study the line bundles on our complex manifolds. But given a K3 surface, the Picard group is isomorphic to Z to R, where R is greater than or equal to 1 and less than or equal to 20. So study all line bundles on a K3 surface is very complicated. So in this work, we will study the line bundles given by the following construction. Since our projective K3 surfaces is projective, so we have an embedding to a projective space. Consider a line bundle on the projective space. All line bundles are of this form. And consider the pullback of this line bundle through the embedding. This construction gives us a line bundle on the K3 surface. That means we are considering line bundles that are the restriction of a line bundle on PM. In other words, we are considering foliations on K3 surfaces with isolated singularities such that the foliation is the restriction is a foliation on PM We are considering foliations on the K3 surface with isolated singularity that are a foliation on PM, and the foliation on PM leaves the K3 surface invariant. That is the idea.
No, you have to prove something.
Sorry.
For the moment, you only assuming that the tangent bundle is the
Okay. Yes. That is true. I'm assuming that the line bundles or the tangent bundle of the foliations are of this form. In this moment, let me remember what is the Poincaré problem. The Poincaré problem is.
Can you prove that it's a foliation that leaves invariant?
Yes. The Poincaré problem states that given a projective subvariety, the idea is to find the foliations on the projective space that leaves the subvariety invariant. So we need that for later. Okay. We have the complex manifolds and we have the line bundles on the complex manifold. Let me fix the first example, a quartic surface in P3. The embedding of the K3 surface in P3, consider a foliation by curves with isolated singularities, and consider that the tangent bundle of the foliation is given by the previous construction. With that, there is this theorem. For D less than 3, there are no foliation by curves with tangent bundle .L. And for D greater than or equal to 3, there are foliation by curves on the K3 surface with that tangent bundle. Indeed, we have an explicit formula for the dimension of the space, for the dimension of the space of the sections that define the foliations. Let me say something here. In this paper, Marcio Suarez solved the Poincaré problem for projective hypersurfaces. So the first part of this theorem is an implication of this paper, but here we solve we prove the theorem with another techniques that allow us have the explicit formula for the dimensions. some explicit examples. Consider the Fermat quartic surface. In this case, the Fermat quartic surface have the Picard rank is 20. That is the biggest possibility of the rank Picard. For D less than 3, there are no foliations. For D equal 3, this vector field defines a foliation by curves with reduced isolated singularities. For D equal 4, this vector field defines foliation with reduced isolated singularities. And in general, for D greater than or equal to 5, this vector field defines a foliation by curves with isolated but not reduced singularities.
So you're saying your first example is unique?
No. This?
Yes.
No. Here we have the dimension of the space is 6. So it is 6. It's not unique. But we have the form of the generators. However, not reduced is not important. The main important hypothesis is isolated. For the following theorem, for D greater than or equal to 6, the foliations by curves on this K3 surface with that tangent bundle are uniquely determined by their singular scheme. So we can study the foliations through the singular points in those cases. What about the other examples? We have an analogous theorem. In all cases, for D less than 3, there are no foliations. For D greater than or equal to 3, there are foliations. And the foliations are uniquely determined by their singular scheme if D is greater than or equal to 6, 5, and 4, respectively. The second and third column are the solution of the Poincaré problem for these surfaces.
Sorry, I think I missed something. So when you say there does not exist for the lower than 3, you are looking for a foliation with a given line.
Yes, with.
Bundle, but you do not prescribe singular set. There are no foliations. There are no foliations in P3 in the first case that leaves the surface invariant. On foliations on P3. There are foliations on P3 for D greater than or equal to 0, but for D equals 0, 1, and 2, there are no foliations that leaves invariant the surface. And so the second column, you have foliation, but they are not determined by the singular set.
Yes. Okay, so we have a solution of the Poincaré problem for these surfaces, and we have the explicit dimension of the spaces that define the foliations. In a more general setting, we consider a smooth complete intersection surface, not K3 surfaces in general. So we have an analogous theorem. If we have a smooth complete intersection surface in Pn with n greater than or equal to 4, if D is greater with the same construction for the tangent bundles of the foliation, is a restriction of a line bundle on the Pm. So for D greater than or equal to this number, there are foliations by curves. And we have an explicit formula in terms of combinatorial numbers for the dimension of the spaces that define the foliation. Let me say something here. In this paper, Marcio Suarez solved the Poincaré problem for
smooth complete intersection varieties with dimension odd. So this is the first case that is not included in this paper. Surfaces. And for D greater than this number, the foliations uniquely determined by singular scheme. That is not exactly in this case, but we have the following. If we have a foliation with D greater than or this number, so if there exists another foliation whose singular scheme contains the singular scheme of the first foliation, that is if and only if there exists a global endomorphism of the tangent bundle of the surface, such that the sections that define the foliations are related with the global endomorphism, and the singular schemes are the same if and only if the global endomorphism is invertible. That is like the result for Hirzebruch surfaces. And what are the future directions? So, in this case, we have that determine the foliations by their singular scheme is related with the existence of global endomorphisms. So, a future work is study the global endomorphisms of the tangent bundle in these surfaces. Study foliations on higher dimensional smooth complete intersection varieties in PM, specifically of dimension even, to complete the problem. We study projective complete intersection K3 surfaces. Another future direction is study projective K3 surfaces, not just complete intersection, through the moduli spaces, for example, and the extension to the results to other Calabi-Yau varieties of higher dimension. And the result, thank you.